So if you have questions, please feel free to interrupt and ask questions as we go. Yeah, so as Jumbo said, I'm going to talk about architecting and regularizing deep convolutional neural networks. So as Jumbo mentioned, in 2012, there's this big revolution in computer vision driven by the success of deep neural networks for tasks like image classification. So here we're showing the AlexNet design from 2012, which stacked convolutional layers for image classification. These concepts are, of course, much older. They date back to the neocognitron from the 1980s and the early success of deep neural networks on things like digit recognition. And since sort of this renaissance in 2012, there's been the proliferation of variations in architecture for deep neural networks for computer vision tasks. So one of the first sort of steps from the AlexNet was this VGG architecture from Andrew Zisserman's group, which sort of made the internal structure of the architecture more uniform, just stacking convolutional layers with small 3x3 receptive fields and stacking many of them interspersed with some pooling operations. There's a network from Google which had multiple sets of filters of different spatial extent at each layer and concatenated those, and also introduced these side paths, which are the dark blue, with intermediate losses to try to assist in training the network. And then more recently, sort of this side path assistance for an additional losses for training very deep networks was shown to be unnecessary if you instead included some type of residual or skip connection that sort of added the results of each successive layer to the representation produced by the layers before it. And these types of networks allow gradients, shortcut paths for gradient propagation during training of the network in an end-to-end manner. Those networks fall for image classification, and most of them have been sort of adapted for tasks that require a richer understanding of the image, like semantic segmentation. A very simple way to convert them is to sort of think of running a image classification type network over the entire image so that you're just classifying every pixel. And this can be done in an efficient manner using some tricks like upsampling and concatenating intermediate layers of a convolutional network. There's also been work on specialized convolution operations for preventing reduction in spatial scale of your representation. So this is the so-called HRU or dilated convolution operations. So you don't have this shrinkage in spatial scale as your network progresses, in which it filter samples from sort of a larger spatial extent. As you can see here, there's also the sort of hypercolumn type strategy in which if you imagine taking all of the layers of the deep network and taking a spatially localized slice through them, concatenating the features along that slice to end up with a sort of per pixel descriptor, and then doing pixel-wise classification based on that descriptor. And then finally, there are these hourglass, UNet, or encoder-decoder type architectures called various names in various places, in which you have a series of convolutional pooling layers, and then another series which reduce spatial scale and increase abstract, while attaining increasingly abstract feature representation, and then follow that by a series of deconvolution, upsampling layers and convolutional layers which restore spatial scale, possibly with skip connection, to end up with a finally full resolution feature descriptor, which you turn into a prediction about scene content. Okay, so this talk is about looking at all these architectural variants and thinking about whether there are design principles that we can distill from them or design principles that we can generalize to create a more general version of them. And the goal is to sort of take an architectural choice and correlate that with some capability of the network itself. So we would like to eventually end up with sort of this black box in which we stick a network. We know, because of how we've designed the network, that it has the capability of solving a bunch of different types of problems. And so we can be confident that when we train that, what is in that box in an end-to-end manner, it'll learn the task. So sort of the first architectural capability that emerged starting with ResNet was integrating some type of skip connection depth-wise. And the capability that you get out of this is really simple. It actually allows you to train extremely deep networks. So training of very deep networks doesn't fail. That's the capability. And then there are a bunch of variety of ways in which you can actually implement these types of skip connections. So the original ResNet, I had some work with co-authors at TTIC on a variant called FractalNet. More recently, there's been another variant of skip connections called DenseNet, which you can think of as ResNet, except the operation is concatenation rather than addition along the skip connections. So all of these alternatives sort of are different ways of granting you this capability of training extremely deep networks. So this first set of capabilities is just making sure you can train a system. Another architectural piece, which I'm going to talk about in detail today, is thinking about connectivity not across depth, but connectivity across spatial scale. And so we want, the idea is to incorporate into the network design scale space, multigrid scale space connections. And we're going to get a couple capabilities out of that. Networks in this manner are going to be able to integrate contextual queues more efficiently. Multigrid connectivity between the nodes in the network is going to allow the network to learn strategies that involve dynamic, data-dependent routing of signals internally to the network. And as a consequence of this, these types of networks are going to be able to learn tasks that require attention in an efficient manner, whereas standard CNN designs standard CNN designs of comparable depth and parameters fail to learn those tasks that require attention. So integrating this type of design sort of gets you better efficiency at standard tasks and is going to unlock the ability of your generic machinery to handle new types of tasks in just an automatic way when trained in standard end-to-end.
So just to clarify,
Yeah.
When you talk about residual or ResNets or
Yeah.
skip connections, you're saying that the issue is not the computational capacity, it's actually the training is easier because you are doing this architecture?
Yes, so it resolves a problem with training, and the problem it resolves is sort of vanishing gradients during a backpropagation. That's one way of thinking about it. And in the FractalNet paper itself, we try to do some analysis in terms of, in this sort of more explicit version of shortcut connections than is in ResNet, demonstrating that it looks like the evolution of FractalNet training is such that the network first learns to use shortcut paths, shorter paths, and then slightly longer paths, and slightly longer paths, so that the shorter paths sort of act as like a scaffolding for training.
So it's not an issue of local minimum, it's an issue of scaling the gradients properly? That's the main thing?
Yes, so the issue of scaling gradients, so there are some other alternative ways in which you may resolve that issue. You think about very careful initializations. You have a near identity initialization. There's some other work discussing that. So you think about it in multiple ways, either handling gradient propagation or gradually transitioning from effectively shallow networks to effectively deep networks. I think both of those views are consistent with what's going on in all of these works.
Could you, before you move ahead, could you
Yeah.
give some sense as to these exciting yellow terms, to what extent are they colloquial and to what extent are they formally rendered? I think it's very confusing.
Okay, so I think residual and skip connections are now sort of standard terminology just because the ResNet paper is so widely cited. Multigrid I'm borrowing multigrid in terms of the term as inspiration from like traditional numeric multigrid methods, and that the sort of computation that unfolds internally to the network is reminiscent of computation unfolding in the sort of a traditional multigrid algorithm. But I'm borrowing that terminology and we're introducing it for this paper with respect to neural networks. I'll show some diagrams later that very obviously there are multiple grids and connections. So I'm introducing that terminology for neural networks here, borrowing it.
So they have
as
architecturally well-defined meaning, but not necessarily mathematically well-formalized meaning. Is that right?
Correct. We're not borrowing the mathematical formalism in terms of traditional multi-grid computation. We're using it as a descriptive term for the architecture here. So this is new work with, relatively new work with collaborators at UC Berkeley that appeared in CVPR 2017. And then the final architectural innovation is a little bit of a stretch to call it architecture, but I mean, it does change the sort of the macro scale architecture of how we're connecting components. And that is to learn a deep model of the label space, of the output space. And we're going to connect this model of the output space up to the network that we're trying to learn in a way in such that it acts as a regularizer. And the capability here is basically that we get free performance. And basically, we spit out networks with better parameters that have the exact same architecture as base networks. But because we're sort of using deep model of both input and output, we can achieve better results. We force the network to understand the output at a more abstract level. And this is brand new work that's in submission now, but has not appeared anywhere yet. Okay, and so the two parts of this talk, I'm going to go into detail about multi-grid architectures and about the work on modeling the label space. Okay, so part one, multi-grid architectures. This is joint work with Sungwei Qi and Stella Yu at UC Berkeley, and it appeared in CVPR 2017. So standard CNN designs, going back to the neocognitron that I showed in the opening slides, and continuing through VGG and residual networks, basically all follow this pattern of taking an image as input at high resolution, pass it through a series of convolutional layers, followed by spatial pooling, max pooling that reduces spatial resolution, followed by more convolution, followed by a reduction in spatial resolution. So at the end of these very deep networks, you end up with a high-dimensional representation that lives on a low-resolution spatial grid. And this works amazingly well, but the fact that it works is not proof that it's actually a good or optimal design. And if you think about this in terms of sort of principles of what makes a good algorithm or what makes for efficient computation, this design actually seems kind of weird because sort of first of all, in terms of representation, it conflates abstraction and scale. So your very abstract representations at the end of the network are forced to live at low spatial resolution. And then there are all these tricks involved if you want to do prediction at higher spatial resolution on all of those networks for restoring spatial resolution that I went through in the opening slides. It's weirdly fine to coarse. So the first thing that this network does is look at a very small section of the input, whatever spatial resolution convolutional filters you have in that first layer. And only later in the network do you have neurons or units that actually receive signal from the entire input. And traditionally, algorithms should be coarse defined if you want to make them efficient. So this seems somewhat nonsensical because of this slow receptive field growth property. It actually may be one of the reasons that we require very deep networks in order to do vision tasks well. Okay, So here's what seems like a more sensible design. Instead of having a single resolution at each layer of the network, we're going to have the network act on a multi-resolution spatial pyramid. The input, in the case of images, is obviously the image at different spatial scales stored on a pyramid, but all of the internal representations the network builds will live on this pyramid. It will just be dependent on whatever parameters the network learns and how it wants to exploit the pyramid. And then we'll extend convolution to act not at a single scale, but across scale space. So convolutional filters now have also a pyramidal shape, and they can evolve, say, across the spatial pyramid. So what I'm showing here is sort of a minimum an analog of 3 by 3 convolution on a pyramid. It's now 3 by 3 by 3, where there are 3 spatial scales involved in convolution. And so it sort of allows the network to choose how to use abstraction and scale, optionally disentangle them. It can store whatever it wants at different spatial resolutions. It's both coarse and fine. There are optionally progressive computation variants of this that I'll discuss that start off at doing computation at only coarse resolution, later integrate fine resolution information. And this slow receptive field growth is replaced by efficient communication in the internal structure of the network, because internal signals can hop up and down scale space as they progress in depth. So essentially, it shortens the connectivity between spatially separated neurons at different depth layers. So this sort of basically just destroys the traditional notion of receptive field in CNNs, because all receptive fields are now going to be essentially data dependent, since any neuron can receive a signal from any other neuron in just the course of a few layers previous to itself. Okay, in terms of how we actually implement multigrid convolution, instead of writing out custom convolutional kernels, we implement an approximate scheme in terms of standard components available in any neural network toolbox. So the idea is that we're going to implement multigrid convolution from one pyramid. It consumes an input pyramid with some C0, C1, C2 feature channels per grid, produces some output pyramid with, again, some arbitrary number of channels per grid that's user specified. And the way this works is that it's going to upsample or sample neighboring representations of neighboring spatial scales, concatenate them, learn a convolutional filter set that acts on the concatenated representation, and then spits out a grid of the appropriate size. So here, upsampling in our implementation is going to be nearest neighbor upsampling, very trivial. Downsampling is max pooling. And because of this, you can think of an entire network now as just a process that unfolds, mapping one pyramid to the next, without necessarily having any explicit spatial reduction stages. So pooling now is a communication mechanism rather than something that permanently summarizes a portion of the input for later layers. So the CNN just evolves representations on spatial pyramids. Yeah. Yeah.
Can you do you get any scale equivariance? So if you have an input which is like bigger in size, does it fire at the right scale or?
Right. So there are multiple variants of this design that would make sense. For example, if you wanted to enforce some type of scale invariance property in the network, you might imagine that you want to tie parameters of these of the convolutional filter sets that act on different scales. In all the experiments I'm going to show today, we're using parameters that are not tied. So the network is essentially free to use this structure in any way it wishes. And that actually may be a better match to data sets themselves that are not actually scale invariant. So it's about exploiting all the information available in a multi-scale representation rather than guaranteeing some scale invariance property of the network. But there are variants of this design where you could make choices related to try to enforce some scale invariance or partial scale invariance or parameter sharing.
A question. So for the initial layer, would then the pyramid be constructed in the usual manner, or?
Yeah. So initially, you can feed in the image at multiple resolutions, or you could feed in just a single fine scale resolution and rely on a couple of these pyramid operations to, since there's an upsampling path here or downsampling path here, the network would automatically build it. In experiments I'm showing, we just feed in the image multi-resolution, so that's easy to do. Yeah.
So naively, one would think that there's a lot more choice on the upsampling than on the downsampling. Is that the wrong way to think about this? Is that
Well, there are potential many choices you could make here. Upsampling, you can also do bilinear, something simple things. Another simple choice. These are really simple choices. If you want to get really complex, you could make the upsampling and downsampling paths mini neural networks that do something on their own, right? So we haven't explored those options yet.
But is it important that downsampling is max pooling, which is nonlinear versus averaging?
We chose, so I'm not sure because we haven't done those extensive experiments. We chose max pooling here for a couple of reasons. One is that it's sort of the natural summarization operation in successful neural network designs. The other is that if you wait a slide, all the standard neural network designs are going to fall out as basically subcomponents of the multigrid network because of our choice of max pooling here, which is sort of an attractive property. Okay, you can build residual units from multigrid networks, just adding residual skip connections between appropriate spatial resolution grids. Right, so then to answer this question, because we have max pooling, you think of this full multigrid CNN, which you might want to attach a multigrid output to or outputs at multiple resolutions to. Every other sort of standard CNN design that I went through at the beginning of the talk is a subset of this. So this is a standard CNN, it's just the multigrid CNN with a bunch of the grids removed. There's a multigrid classification CNN, which shrinks pyramids instead of shrinking grids. UNet is another type of slice through this multigrid CNN. There's a multigrid, you can imagine a multigrid analog of UNet. There are progressive designs which consume a pyramid or a single grid as input, do computation at coarse scales for a while, and then add links from the finer resolutions back in because computation at coarse scale is cheap. And then depending on whether your output is high resolution or low resolution, you might want to prune some of the grids that don't communicate directly with your output.
Each gate has its own number of channels?
Yeah, which is user defined. In experiments I'm going to show, we made the coarse scales really coarse in both resolution and channels. So we halved channels as we halved X and Y spatial resolution. So this makes, in the experiment, it's going to show all of the coarse structure of the network really cheap in terms of parameters and computation. There are other reasonable choices that you might want to make, though. Okay, so just for some quick baseline experiments, we took sort of standard networks like VGG or residual networks, compared their multigrid analogs, which here we're still doing spatial reduction, but spatial reduction of pyramids. We're going to compare these networks on standard image classification tasks. Also, we're going to look at progressive multigrid networks on those standard computation tasks. I'm going to skip through some of these results very quickly. So this is CFAR results, which is a standard image classification data set with 100 different categories. Just reading through the table of results really quickly. Basically, multigrid capacity is useful. It improves performance over standard network designs. It's synergistic with residual connections, so you get a performance gain from having both over just having one or the other. And the progressive versions save parameters and save floating point operations for equivalent or better performance than their non-progressive versions if you compare them setting for a fixed budget of parameters or floating point. Moving on to some more large-scale data sets on ImageNet. We have a 34-layer residual multigrid network outperforms a 50-layer ResNet. And if we want to compare apples to apples at a cap of depth and parameters, we have that it's better to add multi-grid structure to the network than it is to just increase feature channels on a single grid. So here we have wide residual network, which is just residual ResNet with more parameters on each single grid, compared to residual multigrid network of the same depth with fewer parameters, fewer floating point operations, same performance. Okay, we also have some experiments on synthetic semantic segmentation tasks, comparing UNet to just a pure multi-grid network that produces segmentation type output. So this is, we synthesized a synthetic task from MNIST by randomly distorting and pasting overlap digits into a canvas, and then the task is to separate the digits by their original channels. So all the 3 should end up in the 3 channels, all the zeros should end up in the 0 channel of the output. So the top row here is ground truth desired output, and then we have the UNet output, single grid, residual single grid, and then progressive multigrid and residual progressive multigrid. So essentially, the multigrid variants are getting better accuracy on this task as compared to all of the standard designs. Here's another example. Tables in terms of parameters, intersection over union with the ground truth segmentation masks and pixel-wise error. We get big benefits over multigrid, for multigrid over single grid at the same depth. I want to comment here. This okay. These are some speculative comments. This slide is taken from Jeff Hinton's recent paper on capsules, and there's no communication. This work is done completely independently, but the task that they chose to test capsules on is also a synthetic digit separation task. And the title of the paper is, their paper is Dynamic Routing Between Capsules. So they're using this hand-designed module called a capsule for trying to improve the efficiency of neural networks to handle dynamic routing problems. And they also get a performance boost over just standard CNNs for this task. And so the way this works is that they have some explicitly written iterative procedure that sort of determines how neurons at one layer signal, capsules at one layer signal capsules at the next, which is an alternative. This sort of very specific machinery for solving some routing problem internal to the network, whereas multigrid is some very generic design in which routing can be learned. So I just want to sort of draw attention to these possible different solutions to dynamic routing problem. And so, well, obviously one statement is that you may prefer generic machinery. This is not meant as an indictment of capsules at all, because you also may, if you know, for example, certain properties of your task, or that you may actually want to use very task-specific machinery in some instance for things like parameter efficiency. We've not done any explicit comparison of these methods, but I just want to draw attention to these sort of the same inspiration for incorporating changes to the fundamental neural network machinery, which is things like dynamic routing and attention. There may be multiple ways of solving this problem, and it'd be useful to compare and contrast this work in more detail.
So that's very interesting comparison. So the learning of the routing is really that some connections become dead because the weights are zero, or you have other hyperparameters when you connect the...
Yeah, so in the capsules work, there's this sort of agreement type routing procedure. In multigrid, there's nothing special. It's just there are these additional cross-scale space connections. Everything else is just standard convolution. Okay, and then, all right, this is returning back to the multigrid work. This is a synthetic experiment demonstrating actual ability to handle tasks that require attention. So Spatial Transformers was this task, and again, sort of different custom machinery introduced for solving it by Andrew Zisterman's group in 2015. And so the task here is another synthetic task based on digits. You have some digit that's randomly distorted and appears in some location in the input field. task is to estimate the parameters of the distortion and produce the same digit instance in canonical pose in the center of the output. And to solve this task, these authors designed this little module that ran within a neural network and it consisted of a subcomponent that estimated the parameters of the transformation, and then another subcomponent that generated a lookup table or sampling grid according to that was appropriate for inverting that transformation, and then another component that actually applied that sampling grid to the input and produced the output according to the remapped version of the input. So this is sort of a little module designed specifically to handle this task of inverting spatial transformations. So we show that if you just take a network design and instead replace this specific machinery with generic multigrid CNN, you can train the network to do the spatial transformation task in an end-to-end manner. Whereas if you insert a standard CNN of sort of equivalent depth, the network fails to learn the task at all. So here, column-wise is input examples. This is a very simple task. It's just a distorted digit on a white background in some position. Output, same digit instance at the center. Then the next three columns are the UNet, which is encoder-decoder architecture, single grid, residual single grid networks. And then the last two columns are the progressive multigrid and the residual progressive multigrid. So only the multigrid networks succeed at learning this task at all. And even UNet, which consumes the entire input and has the same receptive field as the multigrid networks in terms of receptive field at some internal position or receptive field output, it has the full image as a receptive field. It's unable to solve this task. And so what's actually going wrong with, you're right, so benchmarks, obviously multigrid is necessary. So what's actually going wrong here is that the standard designs don't have the internal communication capacity to coordinate signaling across scale space. And in particular, they cannot coordinate signaling in a way that allows them to learn translation. So here, the top two rows, I'm just showing networks trained when the task is restricted to examples that are rotation only or affine only distortions. All the networks can learn the task fine in that case, but only multi-grid networks are able to learn attention. So the bottom is showing the UNet or encoder-decoder architecture fails to learn translation. So, yeah.
But this, just making the crossing a special transformer and replacing, are you estimating the parameters and resampling or not?
No.
You just select it.
It's just we're inserting this extremely generic machinery.
But then how do you handle rotations if you don't have like rotation copies? In the same way you have like kind of scale copies in the multigrid. How can you learn or how can you write the rotations? Are they in the channels or?
The network has to use its capacity to, network has to use its representational capacity to understand rotation. So you notice that even the standard CNNs can do rotation. So now they might be less efficient than if you had some module that shared parameters between some rotated versions of filters. So you could optionally integrate rotation equivariance into the network design and possibly gain some advantage from that. We're not doing that in any of these experiments though, so the network may have to essentially do duplicate representations of different rotations of subparts. Really what we're showing here is we're trying to push very generic machinery to as many tasks as possible. And so by flipping to multi-grid design, you can push generic machinery to learn translation strategies.
So, I mean, my interpretation of this result is that to get translation, right, probably the generative process of your unit is failing. That you could easily train a network that would give you the kind of center of the digit, right? That's pretty easy. Now, the problem is that you have to copy kind of high resolution images using that shifted map.
Correct.
So if you had the right skip connections in some sense, you could do it.
Right, so the encoder or decoder architecture has skip connections.
But
This
not
is
all
UNet.
long range like this does.
This is UNet with these skip connections between corresponding scales. So those are the side connections there, which is sort of the skip connection UNet design. It may mean that you need sort of multiple passes, or you're right in that you need some effort, signaling effort to coordinate. So I would totally believe that if you, it's possible that if you concatenated UNet with another UNet, made it significantly deeper, you would have the signaling pathways that you needed to coordinate this information transport. And that sort of goes back to this design, this statement that, you know, UNet is some slice. All of these network designs are some slice of the larger multi-grid network design, which includes additional layers, or additional grids at each layer. So if you want to do an ablation study of what signaling pathways are necessary, you could actually start with multi-grid network and start kicking out layers, or kicking out grids to try to discover what signaling pathways it actually use to implement this strategy. That's probably a future experiment that we should do. We did do some experiment trying to look at the receptive fields of units in multi-grid networks compared to the standard UNet. So here we're showing, what we're doing is we're taking input image, we're passing a distractor patch over it, and recording the change at a particular output location. So you're recording the change at the center of the output. And then the magnitude of the change, the stronger the change according to, at a particular location for the distractor, the stronger signal in the attention map at that location. So this builds up a map of how strongly distortion at a particular spatial location affects the output at the center of the image. So this is an attention map for producing the center of the output. And we can also build another attention map for producing a different location in the output. So here, red is attention map for the upper left corner of the output. And what we see is that UNet has this static attentional field. So as you move the location in the digit, the attentional field of UNet doesn't change. The upper left corner of the output, it always attends the upper left corner of the input. Center of the output always attends the center of the input. Multi-grid networks exhibit these weird data-dependent attentional fields that shift with the position of the digit in the input. So there does actually seem to be some data-dependent routing going on here. Okay, so multi-grid seems like a better design on standard tasks in terms of parameter and computational efficiency, and then it is sort of a way to naturally unlock ability to learn dynamic routing and attention functions. Okay, moving on quickly to the second part of the talk, which is shorter. I just want to briefly talk about some new work on regularizing deep networks. This is work with Reza Mostajavi and Greg Sheknovich at TTI Chicago. And here the idea is that deep networks are very supervision hungry currently. Much of the success in vision is driven by having supervised data, and it's expensive to have supervised detailed annotation. So here we're looking at trying to extract additional information from detailed annotation. So the idea is that if we have some semantic segmentation problem, say we want to learn to label cats and grass and maybe some other categories in image. If we only have a few samples, say all of our cats in our training set actually happen to be tigers. We're not able to sufficiently sample the space of cats. A network could simply learn that a cat is it's orange and black striped texture. Every orange and black striped texture, I just label that pixel as a cat. And I'll get 100% on the training set, but of course, that's not the concept we would want the network to learn. It could overfit the tiger. But in the annotated training data, there's actually more structure here that's obvious to any human who just looks at the data. There's shape of these regions. There are common parts that emerge. So there's structure in the annotation that's not being fully exploited. And there are also co-occurrences and scene composition. So what we would like to do is actually extract and use these properties of the detailed annotation while we train the network. And really the inspiration here is some old work in Vision that was sort of doing clustering on the training set to define new subcomponents that you wanted to learn to identify. This is the Poselet work from ICCV 2009, was sort of one of the inspirations. But of course, we're in the deep neural network era where everything is deep network. So the idea is that we're going to break training into two phases, and the first is going to model the ground truth annotation with a deep network, ignoring images. The second phase is going to connect up this model we learned in the first phase to the deep network that we're actually training for the task, and we're going to employ the phase 1 model. It's a regularizer. After training, we can simply discard the regularizer, and we're going to show we get a free performance boost for semantic segmentation. So training phase 1, we have labels as input, labels as output. We don't want to put the identity function in here. What we're going to do instead is use just a simple autoencoder. So this is like a unit-shaped autoencoder, some encoder portion, decoder portion. And the idea is that the capacity constraint between the encoder and decoder is going to force them to learn some abstract compressed representation of label space. Then at the second phase of training, we're going to take that autoencoder, here, okay, this should really be a multigrid CNN, but we haven't joined those two threads of research yet. Here we're going to take a standard CNN with a hypercolumn that is used to produce per pixel predictions. This is sort of the baseline architecture. And then during training, we're going to connect up this auxiliary output path that takes the top of the representation of the top of the network, feeds that into the decoder, which we've frozen during the first phase of training, and also produces a prediction of labels going through the decoder. So you can think of this as an additional constraint that the convolutional neural network, it's free to use whatever strategy and representations it wants for the hypercolumn predictions, but it also has to produce some abstract representation that is compatible with the input of the decoder for producing the labels as output. So we're going to backpropagate from through both of these paths. So the backpropagation through the decoder, it updates the parameters of the CNN, but it does not update the parameters of the decoder. So essentially, the decoding pathway is acting as a regularization force on the parameters of the CNN. And yeah, just this, as a reminder, this decoder is fixed from the first training phase. So we get big training from scratch in a very deep dense net on Pascal semantic segmentation. We get improvement. So here I'm showing output as both auxiliary and primary. Usually at test time, you would drop the auxiliary output. You only care about the primary output. I'm showing both just for visualization purposes. So we can see that the network trained with the decoder as a regularizer basically performs much better than the baseline network. It's able to correct some large-scale mistakes in labels over the baseline. This is training from scratch. So this is training from scratch. We can also train with additional data augmentation and with, so I'm going to skip this. There's an auxiliary regularization scheme where we can also use the encoder as a regularizer. It works not quite as well as the decoder. I can come back to it if there are questions at the end. Just some numbers. Basically, adding this regularization scheme always improves performance, whether tested with data augmentation, without data augmentation, tested on different network architectures. It even improves performance in the case of extremely deep networks. There's a 121-layer dense net trained on with ImageNet pre-training and data augmentation. We still get a performance boost. It's small, but it's still a boost from using the decoder as a regularizer during training. Here we're trying to do some visualization of what's actually learned in the label representation. So I'm showing images here, but really all the queries are done with the corresponding ground truth labels of the set. So this is using the representation produced by the encoder for a particular region in the image to search for neighbors in the training set, neighboring regions in the training set, which have a similar representation of their ground truth labels in label space. So what we want is essentially that it maps to certain parts. What we would hope is that we learn some label representation that maps to that identifies coherent parts of objects, which these queries seem to suggest something like that is going on. So there's actually some useful abstract representation of parts or objects that emerges in the learned label encoder-decoder architecture. Here's some more examples. It's not perfect. There are some failure cases at the end here with a cat paused on being regarded as similar to a car. And also, although you can see in the previous example, we actually seem to latch onto the concept of people and pose in people rather than the specific contents of the scene. Okay, so I'm going to stop there. And this talk's mainly been about enabling new capabilities by making architectural changes to neural networks. The first part through Multigrid, which unlocks dynamic routing and attention, and the second part adding regularization components by using deep models of label structure. I'm happy to take questions.
So the multi-grid CNN learns of the representation distributed across multiple scales across the entire net.
Yes.
It could be that, say you learned something about the high resolutions early on in the net that would have been useful toward the end of the net.
Yeah.
With this architecture, without the skip connections, you're now having to learn this in a very distributed fashion, and these two things at different ends of your net could really be part of the same representation, which you would get if you had the skip connections, but by not having the skip connections, you essentially have to learn the same thing twice.
We do have skip connections throughout the entire multigrid. Yeah, so the entire multigrid network is, in all these experiments, well, except for the sort of ablation studies on CFAR, it's a residual multigrid network. So there's a residual style skip connection from every pyramid to the next pyramid. Yeah, I went through that slide very briefly, but there's the multigrid convolutional side, and then after that, there's the residual multigrid block. And so that's a basic building block. You could use the same thing. Multigrid is sort of independent of the style of skip connections, so you could do the same thing with multigrid dense net. You could create a multigrid dense net or multigrid fractal net. All those skip connections are sort of an independent architectural choice. But yeah, we want the sort of end-to-end, very deep trainability that ResNet or DenseNet or fractal net style skip connections give you.
So in your implementation of the multi-grid net, I was a little confused by how you go from incorporating the higher scales into the lower scales. Because in the sort of the abstract diagram you showed me, it sort of was a wide spread out, but it looked like you downsampled the higher one, which seems to ruin the whole point of it.
No, so we're upsampling the higher one. So I'll go back to that diagram. All right, so this is the multigrid residual unit. So this diagram, we are upsampling. So the higher resolution grid, we're downsampling because we want to match resolution to the output.
Right.
That downsampling is max pooling, though. So you're getting the same information summarization as you get out of max point. But of course, you're also getting the low resolution upsampled for when you're computing the next fine resolution grid. So there's information exchange both ways. And that two-way information exchange is critical. If you just had one-way information exchange from high resolution to low resolution, then you would be stuck in sort of, you would be stuck in that you would be very much restricting the network in terms of what strategies it could learn to implement in terms of information flow.
I'm confused by apparently you're allowing your networks to train themselves to reduce irrelevant layers and restore the architectures that formerly were specialized, if I understood. But I would have thought then that your training times must be much, much, much longer, and they don't seem to be empirically. So is there some design choice that you're making that doesn't show up in the dimension of the parameter space, or is there some other design choice that you're making that I didn't understand in your presentation?
Right. So in images, if you're actually able to efficiently exploit coarse scale information, it may be that, so in terms of like a coarse defined processing pipeline, maybe that you can actually get some advantage from that. And that's borne out in these experiments with ImageNet, in that with comparing this is sort of apples to apples comparison in ImageNet, the residual multigrid versus the plain wide residual. Here we have fewer parameters, fewer floating point operations, same performance, same depth of network. So what it's showing is that the network is actually able to use this to structure a computation in a way that exploits scale space and scale space knowledge somehow to get the same performance for cheaper. So for example, if you have a very coarse view of an image, you may immediately recognize that it's likely to be, say, a scene with a beach with a sky and sand, and then you could condition what filters you run at. You somehow condition the execution at subsequent layers based on that belief. And so that coarse defined processing pipeline might be what you get an advantage out of.
You have some intuition